Yes, okay, we've got a bit wide. That's all right. Gone wide.
Okay, so welcome everybody. I hope you had a good lunch. So now we're starting the session, and we start. Unfortunately, our presenter from Alex and Lucen is delayed, and so we have to start with Sienna, and Simon Parry will have a presentation for us for the next half an hour.
So I have 30 minutes, and I was asked to talk about what Sienna thought about 3 to 5 years out in the future. So that's really the focus of this presentation, that sort of timescale. We do a number of research and education networks, both in Europe, especially in North America. We're one of the major suppliers for people like Internet 2. And these are the sorts of things that we're starting to see and what we keep getting asked as questions. The big thing is the future is unpredictable. The requirements are changing, the world is moving very, very quickly, and if you try and predict out 3 to 5 years, how much is cloud going to take off? How much is CDN going to take off? What's the latest cool protocol? What's the latest technology out there? But the things that are staying is bandwidth is growing. You can pick whichever number you like. Bandwidth is growing either very rapidly or stupidly rapidly. So there's this thing about adding new connectivity and increasing scale. Now, we saw some of the things this morning that certainly some of the service providers are perhaps at a greater scale than some of the research and education networks. But what is absolutely true is you're going to need a lot more capacity over the next few years. On the other hand, we're in a constrained capital environment. Europe is not going to grow from a macroeconomic perspective very much over the next few years, and we have to be able to do this within a fixed capital envelope. And we can't suddenly go and hire another couple of hundred people to come and help run your networks. You know, the Nordinet team is pretty fixed. And then there are these aspirations of things that you would like to do, that you would like to be able to there's a message around speed, that it's the ability to turn up new services, to turn up new capacity quickly. You'll have seen a lot of charts like these from various vendors. Which side shall I go? I'll get this side. Yes, get this side. On the left here we have a relatively standard view of the world at the moment. Whether you're a data center operator, you're a service provider, you have a number of different networks. You have a telephone network, you have one that's usually been specifically built for television or IPTV. And these are all starting to converge perhaps at the optical layer, but as soon as you move away from the optical layer, these are typically sitting on different routers, sitting on different switches, and there's a whole mishmash of technologies in there. The consensus at the moment is that the world is moving to a virtualized infrastructure. If you come into contact with data centers, the whole idea of virtualized servers is now well established. Companies like VMware, Citrix have a number of virtualization solutions. So the compute side of the world has been well virtualized, and it is now pretty much the de facto way of operating a data center, whether it's your own or a cloud operation. You've then also got storage, that Sienna has a very strong partnership with EMC, and companies like EMC would quite happy to virtualize your storage as well. It's perhaps not quite as advanced as the compute side, the virtualization of storage, but that's where the world is. And the connectivity, the network is starting to virtualize. And running over the top of that is a number of different applications. And this change from the vertical model to a virtualized model is something that we're seeing driven out of the IT world, but it's certainly now starting to come across into the network, and especially into WAN. So Sienna has come up with a network architecture. We call it open. I'll explain that in a minute. But the idea here is to focus on everything is growing. You have to stop spending money at the same rate. We have to be able to scale networks. Programmability. Whether you entirely believe that SDN is going to take over the world, a network that's much more responsive, that is virtualizable, that is able to respond to the application things is definitely necessary. And openness. That we are trying to move towards more standardized APIs, more standardized things. This sort of structure only works if these are standardized APIs. If they become vendor specific, then the architecture just simply doesn't work and we all grind to a halt. So Open. Unfortunately, our marketing department have read a maths textbook, so they would like me to tell you that open stands for optical and packet at exponential scale, which is a terrible maths joke, and I wish to shoot my marketing department. But that's what open is about. It's also about the openness of the network. And the three key parts that we talk about are scale, programmability, and application. So scale, we are looking to minimize complexity in the network. That you need some complexity. You need to have places where you bring together routing, where you bring together services, where you want to do fine-grained control of little bits, but you want to minimize the number of locations. As was mentioned this morning, one of the key things about MPLS is the ability that in the core of the network you can be service unaware. You only have to deal with fat aggregates in the core of a network. The layers are converging, devices are converging. You'll see lots of vendors talking about different combinations, but what is definitely true is that no one can manage that many boxes anymore. It has to come down. There has to be some convergence within the network. And Siena's approach is that we would argue about simplifying forwarding, that the only way to scale a network is to get the complexity out of the core and to push the complexity to the edge. It's how the internet scales, it's how the phone network scales, which are the only two large global networks in existence. Programmability, we can't predict the future with absolute accuracy, so when you design your network, when you build out your network, you have to guess. And it's a nice game, and we all make lots of money doing nice network modeling, and it keeps us all busy. But the reality is you have to have a network that will adapt to a new future. Virtualization resources and control planes. Not every network needs a control plane, not every layer needs a control plane, but they are useful, and we have the ability to distribute them, and whether you go through an API or directly on the box, it's all part of that. And applications. At this point, most vendors put up an Apple chart or a Google Play chart and talk about app stores. We're not really talking about that. What we're talking about as an application is a web server or a SIP or something that's an application in the world of networking. Analytics is becoming increasingly important. It's perhaps less so for in the research community, but certainly the service community. There's this thing called money, and money has to change hands, and money has to change hands because there's a contract, and you have to be able to enforce the contract and measure the contract. And at the moment, a lot of SLAs are very wishy-washy, very cause of a lot of arguments. In the NRAN community, perhaps less money changing hands, but this idea that you're providing a service to your customer and that you can exchange for a contract. And openness. Sienna is not the largest player in the telecom space. We have to interop with everyone else. And the only way that we can really do that is by sticking religiously to standards and to open interfaces. Open really sees that there are only two types of network out there, if you boil it down. There is the network that joins the users to the content, and then there's the network that joins the content to the content. There are only these two networks. In fact, one of the charts this morning talked about the three types of network. It separated content into storage and Ethernet. I think that's a mistake. I think they're actually very much from the infrastructure the same type of thing. This is one of the ones for your future work projects this morning. Tony was talking about. Within the service provider community, the most important network to them is how to join users to content, because that's what they do. They're there to join. Within the research community, perhaps more of the emphasis is on joining content to content. These are large pipes, these are aggregates. And they're very different networks because this is about contention. This is about sharing a certain amount of resource between lots of people. This is about paying 20 euros a month for a service. This is about mobility. Over here, this is about static paths between places that you know where they are, but at the same time, the amount of bandwidth will change relatively quickly, that suddenly you want to join one server to another server. That there's a very much a time-based condition. This is all aggregates, and it's probably reasonably static from a network design perspective, that you know how many users are out there. Traffic keeps growing, but the network is a relatively static environment over here. And when I talk about content, that could be anything. That could be a CDN network distributing video. It could be a YouTube content cache. It could be a traditional data center. But as we start to evolve this vision, one of the things that we see is that a content center starts to become a service router. That this is the service aware point, that you're keeping the individual user config separate from the core of the network. So open, two types of network. Drawing this a little more detail because big wishy-washy marketing charts. So at the top you can see a kind of generalized typical service provider network with access coming into the service gateway, whether it's a BNG in the fixed line world or a GSN in the mobile world, connecting off to video servers, CDN networks, public internet, over-the-top video, all the sorts of things that you see in the residential and the mobile network is what we're sort of talking about in terms of use to content. Content to content, VPNs, Core Express, wavelengths, big fat stuff, but starting also to touch large sites, whether this is university, whether this is a large enterprise, that starts to fit within the look at the sort of profile. And this is looking at the types of traffic we've got out there. So this is kind of our big high-level vision about where we're going, and now to try and talk about some of what we're doing about it. Networks are messy. If you go and look at the physicality of a network, the big networks and core networks are typically very, they're not nice rings. They're typically quite meshy or messy, depending on your point of view. But they're highly connected networks. On the other hand, if you look at where IP flows are always heavily centralized. Whether this is coming back onto an IP transit provider where you hand off to the core of the internet, or coming back to a content store, or coming back to a data center, IP flows are very centralized. So somehow you have to map this very hub and spoke architecture onto your fundamentally mesh architecture. And that's what's been causing so much debate in the industry, and why there's so much misalignment and so many vendors coming up with lots and lots of ideas, because this is a very difficult problem. You're trying to map two fundamentally different things onto each other. And the IP stuff, it's about services, about fine touch. Mesh infrastructure is about aggregates and big fat things. Over the last 10 years, there's been a big reaction in the industry against layers. That perhaps going back 10, 15 years, there were a lot of layers in the network, that people would run ATM over SDH over wavelengths, and then try and fit another 3 or 4 layers on top of that. The world has moved on, and the world decided that delayering networks was an important point. And we got to the stage where we're running routers over wavelengths. The pendulum swung too far. The pendulum needs to swing back again, and you need enough layers in your network. 27 layers in your network is the wrong answer. 2 layers in the network is the wrong answer. What's the right answer? A very good question, but it's important to have some layers in there because they do different things. Down at the bottom, because I'm a photon person, let's start at the bottom. Capacity management, big fat pipes. That is what we do. That is CNS strength, 100 gig and beyond. We do big fat pipes. Up at the top, you've got services. IP, and this is where people start. This is where the services are bought, sold. Whether that's a residential IP type service or a point-to-point connectivity ELAN type service, or starting to get into wholesale wavelengths, you've got the services at the top. Routers, they're important. You need to have them, but then again, so is switching. Switching is really important in the network, and it's what got lost over the past 10 years. So Sienna's position, our opinion, is that a strong switching layer is really important. Now, I'm going to be careful here to say, I don't care what technology you put in the switching layer, you probably only need one of them. Whether that's OTN, and you do it as a circuit switched, carrier Ethernet, PVTE, MPLS TP, or MPLS, the traffic engineer MPLS, it's a switching layer. It's come so strong that there are actually vendors coming out with switching boxes. If you look at the one that's mentioned this morning, the Juniper PTX, talking about one of our competitors, they have built a switching box. It's an MPLS LSR. It switches on MPLS tags. It doesn't do routing very well. It's really a switch. And it's starting to come, even from the router vendors are admitting that switching is important and that switching is a necessary part of the network. So we argue that there should be 4 layers in the network. How you choose to implement, is this 1 box? Is this 2 boxes? Is this 4 boxes? Well, that's a tactical thing. But once we've all agreed that switching is important, then we can get on to the debate about what goes inside the same box, how do you communicate, how do you go up and down through the layers. Right, mustn't stand on that cable. So one example, what have we done? Sienna has a strong relationship with EMC. We have, EMC owns VMware. And one of the things we've done is a demonstration, and it's now starting to turn to a product, called Data Center Without Walls. So I don't know how familiar you are with the world of data centers. If I mention vMotion, would everyone know what I meant, or should I explain what vMotion is? Okay. In your server, in a data center now, you run a number of virtual servers. So using a hypervisor like VMware or Citrix Xen or Microsoft Hyper-V, you run a number of virtual servers sitting in within one physical server. That's lovely, that's great. There comes a problem at some point where one of them grows too much and you need to move it. And there's this wonderful concept of being able to move a virtual machine, a virtual server, between physical servers at will. And each of the hypervisor vendors has a tool. VMware's is called vMotion, and it's a GUI. And you can sit there and you can drag and drop your servers around. It's really cool. It's really exciting. And it's very useful it's like network defragmentation, so server defragmentation. You move the server to where it fits. And in fact, they automate it. So you can set it so that every hour it defrags your network and moves your servers around to where they need to be. Brilliant technology. The data center guys love it because it means they can turn off half their servers. The sort of numbers they're talking about is a Windows server typically runs 8% load. So you can stack about 10 of those on one physical machine and throw 9 of your servers away, which is a brilliant idea as far as any data center guys are concerned. The downside is that you need a really good network between those two servers to make it work. That you need to start a gig, preferably a 10 gig network, otherwise it'll take all day. Because you're trying to shove 4 or 5 gig images around and throw them around the network. So you need a good solid network. So some of the stuff that's spoken about this morning is about SPB and Trill and VXLAN and Fabric Path and QFabric and all these things coming out of the vendors is a desperate attempt to try and rebuild the data center network to cope with virtualization of vMotion. What we've done is extended that across the WAN. In your core network, we now listen for the VMware signaling. So as you go to the GUI, you drag your server from one data center to another data center. We snoop on that signaling and re-optimize the network. What we do is use our control plane to flex the bandwidth. This is bandwidth on demand, this is performance on demand, depending on you can flex the network around, and instead of your moving your machine taking 30 minutes, it now takes a few seconds. It's very cool, it's in production, it's being used by a number of service providers, but then we've extended it now to take the storage with it. So with your fiber channel switches, fiber channel arrays, that you can take the storage with you when you move the virtual machine across. Now we happen to do this with OTN because we need the fiber channel. But you could do it with packet. It's a switching layer. It doesn't matter what the technology is. It happens to be OTN, but that's what we used to get this going. If you want, we'd love to sell this to you, but we're not talking about data centers today. But this is where the WAN is going. It's this idea of flexibility, it's about scale, it's about performance. Software-defined networking, I had to mention it at one point. Where we see this going, for us, is that we will build SDN-capable switches. We have OpenFlow on a number of our boxes today. We're going to continue to follow the standards, we're going to continue to follow the work, and all of our equipment will be OpenFlow compatible. Now that's a great statement, because then the question comes of which version of OpenFlow, and I'm going to skate over that point. But we will get there. We're also concentrating really heavily at the control layer, because we have to reconcile a fundamental problem, as was mentioned this morning, was some of our customers are very traditional, who want a network management system that is in complete control. Some of our customers love using our control planes and want a control plane network. We've now got a third class of customers who want to use SDN type interfaces, things like OpenFlow, to run the network. And we somehow have to reconcile these 3 fundamental modes of operation against each other and make them work together in the network. So we're going to have to work really hard on the control layer to be able to integrate all 3 visions of how you should run a network on one system with one set of boxes. What we are not going to do is we are not going to build business applications. We are, we're an infrastructure company. There are plenty of excellent software companies that we will partner with, that we will work with, to do the applications that run through standardized APIs onto the network. Our fundamental thing, we're going to virtualize the network. It's the adaptation onto and off the network, and it's the abstraction, this idea that you can get away, that the applications don't need to know anything about OTN or MPLS TP or PBBTE. They can just get on writing an application through the API that drives down through the network. I could spend hours on this, but I'm not going to. Software-defined networking. We did one of the, in fact, I think it was the first public demonstration of OpenFlow. Was on Sienna equipment. It was one of our boxes called the Core Director, and it was actually an OTN-based OpenFlow demonstration. But 3 years ago, we did a public demonstration of OpenFlow. Bringing that right up to date, last month we took part in a Plug Fest. Hate the term, but that's what the Americans like to call it. And that's looking at, essentially, we brought together at Indiana, at the Indiana University, lots of switch vendors turned up, a couple of control vendors, you can see the list there. I can probably tell you some great stories over beer later about the fun and games that we had. It was remarkable how many different interpretations of OpenFlow 1.0 there was. For what was supposed to be a standard, essentially nobody's kit worked with each other at the first attempt. We had to do some fairly serious software rewrites, but by the end we were provisioning circuits, we were provisioning connections across most of the vendors, and the controller vendors were working, and we actually got a whole load of service and test use case over there. So if people start to talk about OpenFlow as a solved problem, we're at the stage of starting to sort out the standard and do the multi-vendor for OpenFlow 1.0. The standards team, the ONF, are currently working on 1.3 and then OpenFlow 2. So there's quite a big gap between where the standards are and the reality of multi-vendor interop out there. But it's coming, and it's coming reasonably quickly. There's a big industry momentum behind it. The big industry momentum is called Google. And back to the point this morning that if someone weighs you enough money, it's amazing how much the vendors will jump to do stuff for them. Chris Jans really liked his picture. He insisted I put it up there. Okay. Right, that was all packets. That was all Packet World. Let's change subjects rapidly and now talk about optical, which is the other half of Sienna String. Another back to basics thing is Sienna has been at the forefront of the coherent networking revolution. This, in its broadest term, some of you will be very familiar with it, but the broad term is essentially we're stealing a whole lot of ideas from the microwave and radio world and the mobile phone world and applying them to photonic networks. Historically, it's kind of come and gone. Coherence has always been very difficult to do. The thing that changed in about 2005, 2006 is that silicon got good. Is that silicon got really fast, and we can start to actually build some of these infrastructures, some of these ideas out of ordinary silicon. We therefore have moved the adaptation, the sorting out of optics from being an optical world to this is now an electronics problem. And the great thing about it being an electronics problem is that Intel and AMD and Texas Instruments are doing 90% of the R&D for us. We don't have to do anything, we just hang on their coattails and let them get faster and faster because we know silicon is going to get quicker. It's going to get denser, it's going to get better power, lower powered. It just follows the path. And if you read any of the semiconductor things, they've got a 15-year roadmap of where they're going to go next. So we just have to let them go along with it for the ride. But essentially what we're doing is stacking more, using more and more ways about the physics of the optical wave to try and stack more and more information on it. We're using the polarization, we're using the phase, we're using the amplitude, and this is QPSK, but we're now getting to even more advanced modulation schemes as we start to try and wrestle every last bit of information out of Shannon's theory. We are doing spectacular. The other trick is by... Yep.
What do you think about coherent sending in the near future?
Coherent sending?
Yeah. There are some ideas about it. No.
I'd have to go and have a think. Not personally. I don't know if my colleagues are having a think about it. It's a good question. One of the other tricks that we can do is that once we've gone digital, once we've gone electronics with this, we can actually do tricks like we can modify the modulation on the fly. So we're now on our 3rd generation of chipsets. WaveLogic 3 is another marketing department one. The main trick that you can do with this is the one that comes out next month. So the line cards are available with WaveLogic 3 next month. What we'll be able to do is to change the bit rate of the transmission path to do a bandwidth distance trade-off. So you can either go 200 gig over a short distance, 600 kilometers, 100 gig over something longer, 2,500 kilometers, or you can go 50 gig transoceanic, off the same chip, off the same line card. So this will be one card tunable across the whole band that you can just sit there and software change your things. So you can flex the bit rate up and down depending on your line system. You can also bond them together into super channels, which is stealing the term from Infinera, is being able to essentially pack lots of them very tightly into a spectral band. Why do I mention this? I'm trying not to veer into any sales tactics, but the important thing about this is that the photonic layer is now becoming dynamic. That you are now able to change your photonic layer in software. And that opens up some really interesting possibilities. We did, well, Terrainer, this was mentioned this morning. We can go over some really quite insane distances now as we with the same line card, that then you can dial back and take the bit rate up. So we now have this circular trade-off that we can trade off capacity against distance and against the latency. The latency is there that we can actually add a whole load of forward error correction, a whole load of encoding onto the path to make it more resilient, more robust, but it drives the latency up. So depending on the application, is we can apply even more electronics to it, allow it to go further, but at the trade-off of actually losing some of the speed. You now need to start to think about how you can actually use this. How are you going to put this into the network? The way that we're suggesting is the concept of an optical control plane. So this is now starting to sit down right in the layer 0. That you can actually take the performance of the line, look at the performance of how the system is doing, and then go back, work out your link engineering with a path computation engine, and online go and tweak the transmitter. So you can always get the greatest bandwidth out of a link. That has a lot of benefits of its own right, of the fact that you sit there and you get extra bandwidth for free by doing the capacity bandwidth trade-off. But it does drive a really interesting problem, because up and now in your higher layers, you've now got a link that's changing bandwidth. So you have to be able to feed this information up into your layer 1, into your layer 2, into your layer 3, and you start to have to couple the control planes together, so that you can actually feed the information up, so that if you're trying to do guaranteed bandwidth over the top of this, you can start to do some QoS. So there's a lot of work going on at the moment about how you link together the layers of a control plane. So it's a reasonably active area of research. So finally, we were looking 3-5 years out. Okay, let's talk 8 or 10 years out. 2020, it's a round number. Where are we going in 8 or 10 years? This is kind of ambitious, but we'll give it a shot. This is about photonics. Going back into what's now prehistory, late 90s, 10 gig was where it was at. 10 gig was the great thing. Ciena and Nortel led the charge, getting to just over 10 gig in around 2000. I actually worked on a number of products in sort of 2002, 2003, where we did 40 gig, 160 gig, various other high-speed rates, but they overshot the market. The world was not ready. The money ran out. There was a huge bubble that burst. It was good fun going and building 40 gig, 160 gig products back in the early 2000s, but sadly, nobody was going to buy them. So we retrenched. We did this thing, and we did the shift over to digital. The shift over to digital has allowed us to get to 40, 100, and 200 gig in fairly short order. So that's where we are with WaveLogic 1, 2, and 3. What we know how to do, what we have working in the labs, and if you want to come over to Ottawa, we'd love to show you 400 gig and a terabit running today. the terabit stuff is our WaveLogic 5. We have to wait for commercial silicon to become available. It's about the size of a house at the moment, but it is getting smaller. It will go down to being a chip. What stresses me out about this chart is that we seem to be plateauing. Is that whilst we could probably do a 2 terabit and a 4 terabit wavelength if we knew what to do with it, the silicon will probably come, is that they're now starting to fill more and more of the C-band, that we're filling more and more of the bandwidth available to us in the fibre. And it seems to be plateauing. There's a natural top thing that says something around 30 terabits is what we're going to start to top out at, and is the capacity of the system. It looks a bit scary, so let's look at another way. This is a plot of essentially Shannon's limit. What we've got going across the bottom is signal to noise ratio. Coming up here is how much you can pack into the band. Signal to noise is important in this world because fibre is not very linear. Over the sort of distances that we're talking about, there's some big non-linearities. And using optical amplifiers at all in the system means that you inject some noise. And we can kind of trade this off, but we're up against some fairly stiff limits in terms of the amount of power against the amount of noise that we can actually get out of the system. These are our commercial products. These are the ones that we've got running in the lab. And as you can see, we're starting to get really, really close to Shannon's limit. In a practical system, you can't actually ever hit it, but you can get pretty close to it. And if you want an interesting question, is come 10 years' time, are we just going to be able to throw more bandwidth at the problem? Or are we going to have to start to think about how we're using the spectrum more efficiently? How you pack things in, how you do gridless, how you do some of the more interesting ROADM concepts. And then going back up the layers into the packet world, what if we have to start using packets interfaces more effectively? The average router interface currently runs at about 20%, maybe 30%. The average switching interface runs more at sort of 60 or 70%. So that's part of the other reason about moving from routing to switching. That I would really hate to say that it'll never grow more than this, because never say never, because 10 years is a long time, and we'll probably dream up a couple of really good inventions in that time. But we are starting to stare in the same way that in the mobile world, 4G and then 5G is starting to run out of bits. And what you actually just need to do is throw more spectrum at the problem. We're starting to run out of spectrum, in which case you need to throw more fibres at the problem. So if you're looking for some interesting areas of research, there's some stuff coming in about 8 to 10 years that will really change the way the networking works. Okay, so that was me trying to bring it into on half an hour, which is actually where I got to. So do we have any questions?
One question, the last thing you said that the research that is coming is quite interesting. Could that also be some fiber research that we will see some new, where the big leap is coming now that we have to look at our fibers, or pushing the limit of channel?
It's a good question. 10 years ago, I'd have said that a new fibre type may be our solution, and you might be able to go and lay it. But there has been so much fibre laid over the past 20 years that as a commercial vendor, we would find it rather difficult to try and sell a product that required a new fibre. We have to work with, there have been tens of billions of dollars sunk in fibre plant today. And much we'd like to optimise the repeater distance and all the rest of it. 60 to 80 kilometre spacing is what everyone has laid, and that's 15 years ago the equipment could drive the fibre design, but now it's the other way around. You have this huge install base of fibre, and we have to work around it. There are some niche applications. Trading networks, this high frequency trading community are doing some completely mad things. That they are experimenting with the speed of light, which sounds an interesting world. I don't know if you've seen any of the things, but certainly there's between New York and Chicago, there's a huge competition going on for who can have the lowest latency route, to the point that actually someone has strung a microwave link over that entire distance, because the speed of light in air is 50% higher than in fibre. And they're willing. It's not the absolute latency for those guys; it's the relative latency to their competition. So we don't care how long it takes, as long as we're quicker than the person next to us. So there are some ideas of air-cored fibres. They're coming back. Photonic crystal fibres coming back. There's some interesting ideas going on. If it comes from anywhere, it'll be the high-frequency trading community, because those are the guys who are right at the bleeding edge of that world of looking at low latency. But I'm not seeing anything terribly exciting. Actually, there's a London-Frankfurt route that's just been lit up as a microwave link, again for high-frequency trading.
So what about free space optics then?
It was pretty foggy this morning, which is always the problem with free space optics. That it's nice to operate in the near infrared, which is far infrared, where we spend most of our time. That's where all the equipment is. Very, very water sensitive. It comes and goes. I did some work on it in the late 90s in Canada, which was great fun until it snowed, and then we realised that we had to put everything on a 6-foot pole on the roof. Free space optics it's got a really it's starting to come the satellite community, that they're starting to use it certainly up at gigabit class links between satellites as some of the clustering solutions they're doing for remote sensing, synthetic aperture stuff. But terrestrially, until we get around the water problem, and that's a commercial thing. You can find bands that do go through water, but you're in the world of volume economics, that it's a very expensive part. I guess you'd also want to look at what the military are doing. Some of the adaptive mirror technology might be quite interesting. Maybe for 10 years. Never say never. We may all have a glass dome on our roofs. Yes.
There's some people doing research on that in South Africa at the moment, and so we're exploring it in certain links. But obviously, like you said, because of the problems with water and that, we're fortunate we don't have as many overcast and snow days and things as up here. But it can only be considered as an alternative route or a backup link. It can't be the primary link. So but it's a good option in some cases.
I suspect the high frequency trading. I know that there are some free space optical links running around the London rooftops that they discovered. It was quicker but that was quicker to go line of sight between tall buildings than to try and dig up the roads and all the rest of it. But it's pretty niche technology. Cool. These are good questions.
One of your in the first part of the presentation, it was slide with 4 layers.
Yeah.
Or why is IP MPLS required according to your 4 layers? And is switching not capable of handling particular?
You always need some routing. There is always a need for routers in the network. You have to because some of the services are IP based, layer 3 VPNs, IP VPNs, but also quite a lot of especially as you get into residential, the services are demarked by IP address. So a service router is a very much required thing. On the flip side, you still need some core routers. So pause. Going back 10 years, we had the fundamental problem that routers were only ever tested for about 10 to 20 adjacencies. So you could only ever directly connect one router to, depending on the vendor, 10 or 20 other routers. And that drove whole architectures. If you look at for example, the BT21CN model, that whole architecture is driven by how many routers you can connect to other routers. As a result, they've got 400 core routers that connect to each other and to nothing else. The world has moved on a long way in 10 years. CPUs have got better. There's a test report, I'll try and dig you out the link, of Alu's 7750, where it can now form 2,000 adjacencies. So it's really moved on. So this idea that you need lots of core routers to scale your network has gone away. A core network, or a few core routers, is really important because they solve the n-squared adjacency problem from your service gateways. but we're seeing networks, and in fact, vendors, not just Ciena, are producing products like the PTX, like the ASX, that are optimized for this idea of very large core routers and then a whole lot of service routers, and they're really diverging in terms of product families and where the vendors are going. The requirement is very much splitting. So you will need some routers in there, otherwise your IP guys will get bored.
Was there another IP layer on top of your IP?
No, that was really trying to avoid duplicate layers. Yes.
Okay. But IP MPLS is required between all the routers.
Yes. You need the MPLS for traffic engineering. Otherwise, you can't do resilient paths and all the rest of it with just IP. As we saw this morning, convergence times of raw IP are not great. And that's an interesting development because that's being driven as a reaction to some of the other limitations. That, for once, at least, is not coming out of data centers. People aren't trying to route data centers again. We did that 15 years ago.
Okay, thank you.
Okay.
For the presentation. The next presentation is Chris Liu from Infinera.
So there were some problems with his presentation. Was that moved? Let's see if yours moved. His presentation. Let's see if yours is center. It seems like a from there.
Oh yeah, that's kind of close on the edge there.
I don't know. It seems okay.
Yeah, I think that's good. Okay. Okay. My name again is Chris Liu. I'm from Infinera, and for those of you who are unfamiliar with Infinera, we, like Ciena, are a provider of optical transport systems. Our differentiator is that we've developed a photonic integrated circuit back in 2001, and we leveraged that technology in order to develop converged platforms like the DTN and DTNX. And what I'm planning on talking about today is sharing our perspectives on how the core networks are evolving. So talk a little bit more about network architectures and the sort of the changes that we're seeing in the industry. So first I thought I'd start off with a few observations that we're seeing. First of all, as you're very, very well familiar with all the demand for traffic, there's obviously a need for more bandwidth to be carried across the fiber infrastructures. Today you're seeing a large number of 100 gigabit wavelength deployments. In fact, Infinera just announced that in this past quarter we've shipped more 100 gig wavelengths than any other transport vendor. So that is a testament to the growth and interest in 100 gigabit wavelength technologies. And in order to scale the capacities beyond the 8 to 10 terabit range, we're seeing an evolution towards super channels that we just heard about. So we're already doing a lot of development in 500 gigabit and terabit super channels in order to increase the fiber capacity. But along with this observation is that the bandwidth services themselves are not evolving at the same rate as the wavelength technologies. Bandwidth services today in carrier core networks are still largely 10 gigabit. We even see some 40 gigabit, and now 100 gigabit Ethernet is emerging as a new service type. But right now we're seeing the demand for capacity outstripping the rate at which these services are growing. So the reality is you have a network that requires more fiber capacity, but you also have a mix of different types of services that need to be transported over that infrastructure. And for that reason, we've been talking with a number of folks in the industry. It's really important to start with thinking about how to decouple the services from the actual optical transport technologies in order to maximize the flexibility of these networks. Because ultimately, as we get to terabit super channels, one cannot expect terabit Ethernet to be prevalent across all these different networks. Like every other network that we see in the world, there's obviously CapEx pressures. The current practice of deploying bigger, faster, larger routers to support larger networks is not scaling. It's not scaling from a capital expenditure perspective. It's not scaling from an operational perspective. And so many are asking the industry what are some different ways or architectures that will help us build simpler networks that that simplify both the cost of those networks as well as the cost of running those networks. Bandwidth services continue to be unpredictable. It's very hard for any service provider or network provider to try to estimate exactly where traffic is going to be needed when. And the evolution of cloud is obviously going to be impacting that further as things become even on more demand basis. Bandwidth will be required between places which are very hard to predict. And even in today's world, the cost per switched gigabit in transport is still much smaller than the cost of switching packets, for example, through IP cores. So can we leverage that disparity in cost in order to develop an architecture that further reduces the cost of not just individual packet layer, individual optical layers, but of the total network solution? And what we're seeing is there's an ample opportunity here to design different architectures in order to take advantage of this cost differential between the different layers of the network. And finally, while technology-wise there is no real issue in developing control planes that enable interoperability between multiple domains, multiple vendors, and even multiple layers of the network, it still seems to be elusive. For an example would be the GMPLS Uni technology that was developed probably more than 10 years ago in the standards bodies. To my knowledge, it still has not been commercially deployed. And as you well know, there are some new emerging approaches to control plane technologies like SDN, which potentially can have an impact on achieving the goal of providing services across these different layers, domains, as well as different vendors. So this is just a simple graphic illustrating, with the old practice of building networks, you had a separate hardware box for each of the networking layer functions. Obviously, that worked in the past, but with the continuing pressure of economics, one cannot sustain this, moving forwards. One cannot keep adding hardware boxes to solve the problem, because not only does it lead to excessive costs, but you've got multiple operational challenges in dealing with different vendors at different layers, and now you've got multiple domains to deal with as well. So it's not a very scalable model to continue to try to grow each of these systems to have more switching capacity or higher rate interfaces. That's not quite the approach that we see as the right way to build scalable networks. Common practice today is to build everything into the IP layer. We like to refer to this sometimes as the all of your eggs in one basket approach, right? Try to relegate not only all the services, but all the bandwidth management functions, such as supporting switching and grooming and protection. Put that all in the core router and rely on dumb optics in order to build networks. That worked in the past, but again, it's not very scalable. The IP layer is becoming too bloated with too many different protocols to try to support every possible potential networking function. And in our perspective, the optical network, meanwhile, is becoming much more flexible with integrated switching capabilities. Why aren't we yet leveraging those capabilities to simplify the network and offload some of the costs that are that exist within the IP layer? Furthermore, and this is probably one of the reasons why SDN interest has taken off, the control plane within these routers often locks the services into that particular vendor's implementation within a particular domain. So even though it's great for supporting certain features and services within a domain, rarely will you find any sort of control plane capability that exists across multiple domains and multiple vendors. We're still also seeing the independent layers operating in isolation of each other. Clearly, if the IP layer had more information about the topology of the transport layer, for example, could make more intelligent decisions. And the current practice of throwing bandwidth at the problem in order to scale the network is not very cost effective. There are still many redundant A+B router networks out there that have at most 50% utilization. That is not an efficient use of capital. So here's a couple of different interesting scenarios. What if it were possible to flexibly create your network slices on the fly between the different layers of the network? What if it were possible to create network connections over these multi-domain, multi-layer networks all automatically and roll out services a lot more quickly? There's been a lot of activity in this area of SDN to try to virtualize a lot of these networking functions and make it much more flexible and easily to deploy networking capabilities without having to always roll out some sort of hardware platform box out there. And I think all of this is very interesting because it begs a question of how do you achieve all this type of flexibility and scalability while still trying to simultaneously minimize the total network cost. And so it's no longer about trying to minimize the cost of a transponder or minimize the cost of router port. It's really what's the best way of looking at all the different capabilities of the different networking layers and figuring out a way to make networks much more flexible and economical. So here are some of the key challenges that we're seeing in the core networks today. One is, how can bandwidth evolve towards more of a bandwidth utility model? Today bandwidth is very much a static resource you assign on a point-to-point basis. It's there whether you're using it or not. Electricity or water follow more of the utility model, where on an on-demand basis you can request that resource, and when it's not being used, it can be used by someone else. Okay, that model has worked very well in cloud computing. Can we bring those concepts of virtualization to the optical transport world and provide scalable bandwidth wherever and whenever it's needed? Another question is how do we rapidly deliver this bandwidth? Now, certainly within any particular vendor's domain, there are solutions today, whether they be network management based or embedded control plane based, to turn up a circuit from one edge of that domain to the other edge of the domain. How do you do that now in a more complex network like in the NREN community, when you've got multiple domains, multiple vendors, and ensure that you still are providing for the agreed upon performance levels, that you're able to do so with minimal operational expenses? Service ubiquity is also a key challenge, right? You've got different domain networks spanning Europe, and you need to deliver services potentially from anywhere to anywhere, although I would think some of the research centers aren't likely to move anytime in the near future, but there might be experiments or data that you need to move around on an on-demand basis. Wouldn't it be great to have this service be ubiquitous without over-provisioning or over-dimensioning your network in order to provide that? And then lastly, programmability. We also, like Sienna, view this as a very key important part of enabling some of these new network architectures. What are the right types of interfaces to support on a platform that will help enable these technologies to be well integrated into what's happening in the IT world? So one of the concepts I'm going to talk about a little bit more is network virtualization. What are some of the key ingredients in order to make this happen? And so, one simple vision for the network, which I think applies, is that what we want that transport network to provide to applications and to higher layers of the network is this concept of an infinite pool of intelligent bandwidth, right? This already smells like abstraction. How do you, with all the different technologies that are out there, how do you provide this type of vision? We obviously want to provide WDM capacity wherever and whenever it's needed, but we don't want to have necessarily require you to pay for that up front. Right? Obviously, when you buy the fiber or lease the fiber, it would be great if it were already pre-equipped with 8 terabits of capacity, right? Because then you can really enable this bandwidth on demand model. But the reality is you can't enable 8 terabits of bandwidth on a fiber until you buy the actual transponders. So is there a model out there where you can actually demand capacity whenever you need it? And on top of that, then you can provision your bandwidth on demand. One of the concepts there that we think is going to be important is virtualizing that optical wavelength capacity. Today, networks are still largely 10 gigabit wavelength based. We're seeing the deployment of 100 gigabit wavelength technology, but I guarantee in a few years you're going to see 400 or 500 gigabit super channels or terabit wavelengths deployed in a network. The last thing you want to do is have to re-architect all the higher layers just because the technology changed underneath. So having the right abstraction is important because you want to be able to support whatever your research applications require from a bandwidth perspective, independent of what NREN has deployed technology-wise in their optical domain. Automation, reliability, again, a lot of the resiliency in today's networks are implemented in layer 3. We think there's a huge opportunity to leverage some of the new shared mesh protection schemes in layer 1 to offload some of that responsibility from the more expensive routing layers. And how do you do this? Essentially, follow the computing model and virtualization. Is there a way to do this also for the optical domain in order to make bandwidth much more of a utility than a static resource as it is today? So what are some of the key ingredients? This is not an exhaustive list. Again, this is some of the key points I think are important for our discussions tomorrow when we're collaborating. First is you need to have scalable and flexible optical transmission capacity. So we're already seeing an evolution from 100 gigabit wavelength technology towards super channels. We're seeing much more flexible allocation of optical spectrum in order to support higher capacities. That's going to be important, as well as the ability to redirect optical capacity to destinations in a network where they're required. I mentioned earlier, in addition to just bandwidth on demand, it's going to be important for carriers to also have capacity enabled through a point-and-click mechanism, because at some point it doesn't become cost-effective to continually roll out trucks in order to deploy wavelength upon wavelength. So is there some means in order to instantly request bandwidth be available on the fiber so that you can start provisioning your services? Now, our belief that in order to make the transport network that agile and that flexible, you really do need to have a multi-tiered transport switching architecture. And so this means not just having the ROADM type capabilities in order to redirect portions of your optical spectrum, whether it be a wavelength or a super channel, but also having the agility that digital switching can provide in order to groom and switch circuits onto those wavelengths, such as via OTN technologies or integrated packet switching technologies. Both of those are going to play important roles. We also still think that it's very important to address the multi-vendor, multi-domain, and multi-layer networking problem. Control plane are still progressing, within the IETF and within ONF. There's new work that's being done in order to make the multi-layers talk to each other. But with SDN now emerging, this could also potentially be an important tool in supporting the provisioning of services across these different heterogeneous types of networks. And lastly, there's been a lot of investment put into GMPLS as an automated discovery and routing protocol for the transport layers. While the original SDN concept for packet systems was to completely decouple control plane from the forwarding plane, we see that GMPLS actually plays very well with the SDN concept, and so Infinera, along with others, are working within the confines of ONF in order to define the right levels of abstraction for customers who still want to continue to leverage our programmable GMPLS capabilities in setting up services across the optical domain. In order to satisfy all these different types of requirements, though, it is our strong belief that convergence is necessary, and that is the integration of multiple different networking layer functions into single systems, so in order to reduce the cost and to simplify the operations of the network. So this is just an example of what the hierarchical bandwidth management architecture would look like for a particular core networking site. There's both the requirements for managing the optical capacity at those locations, which is be able to switch super channels or wavelengths from one fiber direction to the other without having to break it out into the electronics domain. And like Sienna, we've also developed flexible configuration capabilities at the transmission layer. So customers today can trade off capacity for reach by merely software selecting the appropriate modulation schemes on the system. We also think that it's important for these systems to support optical restoration. Now, I do not believe you'll be able to achieve the same level of performance that you can with digitally switched systems, but we think that it's important to have different protection schemes at different layers so that you can support different levels of resiliency in the network. It's not always the case that you're going to have digital switching everywhere in the network. But along the optical bandwidth management capabilities at those sites, we also feel it's important architecturally to have the appropriate amount of digital switching available. And our belief there is it's really going to be a mix of OTN, circuit-based switching technology, along with integrated packet switching technologies. Now, we're not talking about building the equivalent of an IP router into these systems. What we're talking about here is building just enough packet functionality to efficiently switch packets that happen to be transiting those core sites. So in these types of systems, you can easily configure the systems to have any amount of OTN or packet switching capability. And in a packet case, the system would be acting more as an MPLS LSR. These systems similarly will also have integrated protection and switching capabilities, both dedicated protection schemes as well as support for the new emerging standard around shared mesh restoration. And it'd be great if you can migrate some of that protection capability out of the IP layer and let the IP layer run at much higher utilization rates by leveraging some of the integrated protection capabilities in the transport layer. So architecturally, on the left, is sort of the conventional approach that I mentioned earlier. We're already seeing the results of phase 1 happening, which is the convergence of your traditional circuit-based switching technologies into the transport layer. We see a large scale deployment of these converged OTN WDM systems today. What we're seeing in the IP layer, as you well know, is this divergence, right? We're starting to see the core routing market separate into IP routers, and separately there'll be MPLS LSR specific type switching platforms like Juniper's PTX, which can be used at core locations where you don't need to do a lot of IP switching, and which should provide for improved economics. Longer term, though, what we see is obviously is still the importance and requirement for having IP routing in the network, but a further convergence in order to further extract cost reductions in the network, which is the integration of MPLS and MPLS-TP switching functions into those transport systems. So this is sort of the trend that we're seeing in the industry today. And additionally, we also believe that this concept that SDN and the inertia that SDN has is very relevant to the transport domain as well. As I mentioned, there's already a working group in formation within the the Open Networking Foundation in order to start defining what transport SDN is all about. But just as you have in the routing world, in the optical transmission world, there's going to be this pool of physical resources, whether it be a mix of optical wavelength technology, OTN, or packet switching technologies. And we similarly have multi-vendor, multi-domain types of issues. But what the ONF is working on is defining the right level of functions and abstractions of this technology so that we can present a uniform interface to the applications who just want to provide and request bandwidth, between different locations in the network. And so right now there's discussion around this concept of an OTS, an open transport switch, which is a virtual switch software application that can run on transport systems or actually run anywhere in the network, that provides the right levels of abstractions to these applications in order to achieve much more flexible bandwidth, automate operations, improve the utilization of resources in the network, and to also speed the deployment of new services in the network. So we think this has some promise, but as you know, it's still early on in the evolution. Standards are still being formulated, and not all the problems obviously have been addressed yet, but it does provide a potentially new tool and a toolkit for solving some of these challenges. So just to summarize here, it's and we've talked to a number of service providers and content providers in the space. A lot of them agree that this just conventional approach of just using IP routers everywhere is not something that scales. Even though the routers are getting bigger, the cost efficiencies are not materializing. 100 gigabit Ethernet router ports are not 4 or 5 times 10 gigabit Ethernet router ports. And on top of that, the cost of switching a bit through a routing system is still a lot more expensive than switching bits through transport systems. And over provisioning your networks just to handle peak scenarios that you envision is often resulting in just excessive underutilized capacity in the network. We believe that with the emergence of a lot of this new switching functionality in the transport layer that gives this new level of agility, there's certainly ample opportunity to leverage those capabilities to design better networks. And we're already doing a number of studies of what are the results, or quantifying the results of increasing the meshiness, within your routing network, increasing those adjacencies, and seeing how transport technologies can be applied towards those network designs in order to lower the cost. And lastly, there's now this potentially new alternative approach to solving some of the more complex networking issues that you folks are experiencing. For example, multi-domain networking. I think it's important to continue our research and support for multi-domain, multi-vendor embedded control planes, but there seems to be a reluctance in the industry to really adopt that, embrace it, and deploy it commercially. And hopefully SDN can help maybe address some of those issues by taking the problem out of the multi-vendor interoperability domain and letting other vendors sort of build those types of applications to open interfaces that vendors like Infinera will support. Okay, so with that, if there are any questions I can answer. Good. On that question of free space optics that was earlier, the New York to Chicago route does not require a huge amount of capacity to support high-frequency trading, so microwave is perfectly sufficient because they only need about a gigabit per second to support that kind of application. But for mass market distribution, yes, 10 gig and eventually 100 gigabit services are going to be required. So I think maybe free space optics may have a role in that, but I think right now what we're seeing is more of the microwave approach. Okay, thank you.
Question.
Yeah.
You talked about the flexible network, and in order to deliver flexible bandwidth. To do that, you need maybe bandwidth variable transceiver which can you adjust the bandwidth or the modulation,
right,
and so on. What's Infinera do it about the bandwidth variable?
Yeah, so we have a flex coherent technology that's already deployed within our networks, which allows you to change that. So if you've got some very long reach applications, you can switch from QPSK to BPSK, extend the reach, but it will also affect the total capacity on the receiver side of your transmitter. So that's also DSP based technology.
So you can do that. What range, what bandwidth range you can adjust the transceiver? Is it you can, what about the bit rate? You can adjust it from 0 to somehow?
They're fixed, fixed discrete modes, and based on the modulation scheme that predefines the actual bit rate of the
Could
super
be
channels.
Any modulation or?
No, there's a fixed set of, and maybe Jeff can chime in on what the different modulation schemes are, but there's a fixed number of modulation schemes. You pick one and it predefines the total bit rate of that super channel.
Yeah, we could probably take that offline if it's not of interest to general people, but each individual carrier can be separately modulated as well. So it's not quite as simple as saying there are, say, 2 speeds for the super channel transponder. Each individual carrier can be modulated.
Which is something which is in development or something
No,
which
it's already
is
deployed.
already there?
Yeah, you've got it actually. The Dante background has it.
Well, it's being solved, so we're jolly.
Okay.
Okay,
Thank you very much, Chris.
Sure.
So next speaker is from Alcatel-Lucent, Liven de Port. We finally made it. We finally
It's Liven
Liven de Port.
Yeah, it's a French name.
Yeah.
Oh, okay. There's one.
So I think you need this one.
Yeah, you got mine.
So don't you have
Yeah, I misbooked my flight. It's here.
You made it, that's the good.
Yeah. Right. Okay, so my name is Lieven Levro. I apologize for being late. Well, on time, thanks to swapping out. Thank you guys, appreciate it. So I was asked to come talk a little bit about IP and optics evolution, and I just heard the last part of the Infinera folks, but I realized that the topic is so broad and so big that it's very difficult to actually, and I have half an hour like everybody else, so it's going to be either I will have to talk very fast, which I can do, I promise you, but I won't do, and I picked a few things that I think are of interest, the things that we're thinking about. I heard SDN is one of them. So let's talk. I was thinking of talking more. My presentation might divert on what I say a bit more, but so basically, why do we want to do that? I heard it. Why do we want to do integration of IP and optics? Is it because it's sexy? Is it because it's somebody's? Oh, we are all talking about it in the industry, as is SDN lately. And actually, we thought about this 3 or 4 years ago. When customers were telling us, they're saying, listen, you come with 2 teams. You come with the optics RF, an RFP and RFI reply, and you come with the IP RFI reply. Why? Why don't you guys work together? And we thought, shit, this is bad. If customers tell us that we need to work together, we're doing something wrong. We have solved this now. We're now one team. But in the meanwhile, we started thinking about how we can work together, interoperability. Jeff, you used to work for Bay Networks. There was sometimes, long time ago, spanning tree. Nortel and Bay Networks spanning tree wouldn't work together. It was one company. You go like, you know, that can't be, right? So you really want to fix these type of things, interoperability. So why again? Why do we want it? Why do we want to do it? Well, if you think about network layers, if you think about the cakes, the layering in a cake, for example, you want to make, and this is not for tasty things, but you really want to make to a minimum set of network layers, because each network layer comes with an operational aspect. You have network management, you have a control plane, and you have a data plane, and they might be different, because remember, the control plane, you have circuit switched and you have packet switched, and these are different things. They're really truly different animals. And integrating them is sometimes is a bit challenging, I think. So if the more layers you have, the more network management systems you have, the more control planes you have, and the more operational costs you have. Now that might not always be a problem for you guys, but in the service provider world, that's where you really want to squeeze out the network layers, the cost, to reduce the cost, and put the adaptations in ITU talk, the adaptations at the far end. You know, an adaptation like a pseudo wire, you adapt the client signal into something that you can transport over a common infrastructure. Still leaves us with the problem, is it going to be packet switched or circuit switched? And that's where a little bit the problem lies, i.e. some people say, what do I need to do? Do I do this or that? Do I put an ODU grooming switch? And where do I put it? I don't know. I mean, this is where the modeling comes in. But modeling needs to do it intelligently. You need to have the proper tools. And you also need to think about, well, how is my traffic going to evolve? Am I going to expand fibers? But probably not. But am I going to have more pops, more bandwidth left and right? How is it going to evolve? Magic. we need to look into that ball, difficult. But these are the parameters I'm always asking. Give me your traffic matrix, what you have on each network layer, on each service, if you have alien waves, if you have a TDM, if you have SDH, ATM, or even X25, whatever. Give me the traffic matrix on each network layer, IP MPLS, I forgot, and we will then, and the topology, and where you want what, that leave us do that. And we have these tools that actually automatically can say, listen, if you do an ODU switch here, what grooming do you want? ODU 2 to 3 to 4? Oh, no, my cost goes up. That's not a good idea. Oh, wait a minute. If I do put it there, my cost goes up, but my resiliency increases. That's good, because I then have better SLA that I can have. So there is a whole thing about tools and network layering. Sorry, I started off with network layering, but the tools can help you answer the question where to do what. Now, that is one, I think that's a pretty good reason to kind of have a look at where you can optimize. Again, you know, this is in the industry typically what we do. Now, like I told you, I'm just touching up on a few points, is that if you think about it, you made up your mind, you want to have an OCH, G709, or WDM network layer. Great, you're all happy. You still need to think that it might have a control plane. Which one would that be? Well, let's SDN for the moment let's leave SDN out of the picture for the moment. But it could, for example, be GMPLS. We know GMPLS, we love it to bits and pieces for a long time, very long time. You know, we have deployments, but it's not like IP MPLS network deployments, let's be honest. So that is, but we have the control plane, let's use that. Now, that is typically used for circuit switch technologies. TDM, lambdas, you name it. But, and also, well, no, hang on, packet switch is IP MPLS. IP for, well, actually for two things. The more I talk about it, the more I get it, understand it, it's funny, is that IP for the IP control plane, but also embedded in the data plane, which in GMPLS we know is separated. The control plane talks over things that it can't identify, i.e. I can't give an IP address on it. So you see, it's all GMPLS, but it's slightly different. We need to understand that. Sugar, how are we going to bind them together? We need to glue them together. We cannot have an IP MPLS network and a GMPLS network and another one, and they want to talk, and we go like, how do we do that? A lot of discussion has happened in the last IETF between Cisco. Well, Cisco is everywhere, which is not a you know, that's not a surprise. But Cisco, Juniper, ourselves. I think you guys were there as well. Basically, how are we going to glue it together? And there are two actually, two views. One is the UNI and the overlay. Let's not talk about the overlay, but you have two views on doing that. So the answer is UNI, because you do not want to have visibility. You want to have minimum set of function configuration things you want to do on the router and the optical cross connect that interconnects those two control planes. You want to have as less as possible. And there are actually two options. I can explain later, but like I said, I don't have the time, mind me. So let's agree that we have GMPLS and IP MPLS, and we use a UNI. So let's say that we solve that problem. That's good. One step back. We looked at our customer base, and actually we came out with kind of four, and I'm talking about customers worldwide, we came out with 4 sets. People that are hardcore and say, I want a single box and I want to put everything in there. ODU grooming, ODU switching, G709, optical switching, I want to do packet switching, full IP MPLS core, then maybe with some configuration issues I can only make an LSR only, but I want everything in a switch, everything in one chassis. It might be a big chassis, but I want everything in there. That's one set of customers. The other set of customers goes like, we actually do not care whether it's all separate chassis, but we want to manage each network layer separate. Think about the big ones, the AT&Ts, for example. They have a massive people headcount assigned to manage these network layers individually, putting them together. Ultimately, nirvana-wise, hell yes, they want it, but is it going to happen from today to tomorrow? No. So those are the other set of people, of customers, sorry, not people. And then you have 2 intermediate sets. People that say, listen, I understand that if you want to integrate a transponder, high bit rate, let's say 100 gig, into a router, my slot economics don't make sense. Slot economics, new keyword, meaning the backplane connectivity I have towards the switch, packet switch, and the front plane axis or the bandwidth I can have on the axis don't really match up. I can give you an example. For example, for our IP product, we have one transponder, one MDA, and it's about this big. I can put two. The backplane has 200 gig. 200. Oh, and 20. I have a transponder of 20 gig. Of course, I can 2,000 kilometers far, but I pay for backplane capacity that is not usable, and I still need to have the switching matrices in there. So the economics, the bandwidth slot economics don't make sense. So how are we going to solve that? Well, one of the things we talked about is actually, or thinking about, is putting those bulky things outside the box. Kick them out. Put them in a chassis, separate. And that's where the two customers come in. One customer says, I understand that, and I'm a packet guy. I really have a significant amount, all my services are packet based. But I want to configure that transponder as if it is integrated into that router. So we call that the single NE, single network element. It's a multi-shelf, but it's a single NE. So I log onto the box, I do show port, I see all the ports. I can do fault correlation, I can show the alarms, everything is linked. That's one. Customers want that, packet-based, packet services, router guys. They really they love their CLI. Yes, they will use a network management to configure the service, but when the S word hits the fan, they go to CLI. What is my OSPF? They want to see the port data. Oh, I see errors there. They want to see, oh, PFD just went down. Why? They want to have the CLI inside. The other guys, they are kind of a little bit less than AT&T. They understand, like, Bomber, if you really want to reduce cost, we only not need to do it in the network. We also need to adhere and adapt this merging of layers in our operational model as well. And those customers, they say, we understand we want to go together, but we cannot simply go first, second. There is also the aspect for those customers that we have a significant amount of packet services on the packet layer, but we still have a significant amount of TDM services, legacy. Can you switch it? No. What is in those legacy packets? No, you cannot break them out. You need to transport it as legacy, whatever it is. Okay, well, shit, now what do we do? Well, that's where we have the control plane that I started about, is that I keep two boxes. I have two separate network management element managers in there, but I put the control plane, or the integration is based on the GMPLS control plane. So those are the two differences that we see. Now, why am I saying this? And I'm stuck on my first slide, and I've run through, 20 minutes already? 15. The reason I'm saying that is that it is important to analyze for us to be able to set our sales for sure. I say it wrong. Is that we need to look what our customers want, how they work, how they think, how they operate, so we can build products or products that actually can be put in multiple facets, in multiple of these networks. I.e., if we put, for example, we have just launched, a while back, a big huge router now. Well, it's a core router. What I want to say is that, and we want to make sure that we can put it in any of these any of these customers. That's basically the reason why I'm telling you this. Now, if you want to read this, please go ahead. You will get the slides later. Now, the IP optical, what is important for us? First of all, I'll start with the simple things. Integrated management. We have that today, is that I can from a network management, I can provision a trail. I can put a wave tracker key on it, so I can do some smart photonic, I'll repeat that, photonic OEM. It's a photonic OEM's way of doing it. So every transponder that Alcatel-Lucent ships will be able to do that photonic OEM, given that the line system is also from Alcatel-Lucent. So we can actually, these two things tie into our SAN. We can provision a Lambda, we can provision an IP MPLS, we can provision the services, the IP MPLS services, whatever it is, VPNs, VPLS, E-pipes, whatever. So that's all tied together. The second thing is that we are now on the XRS, for example, we have an OOS, and here it makes sense to say OOS. I mean, in these, how can I say, Nordic-speaking countries, in the America they don't understand, but OOS, optical extension shelf. Optical extension shelf, I can hook it into an optical extension shelf, R1830. We manage it as a single network element. So that is a quite important thing for us. It's just an Ethernet port at the end of the day, but the logic and the software behind it is not just. That's a little bit more complex. And then the other thing we have is that we have the offloading capabilities. Like I said, with the tools, you can actually say, and that's where SDN I think is going to play a big role. With the tools, we can actually have a quicker look and say, well, hang on a minute, doesn't it make sense to actually do 100 gig or bring the 100 gig to a central point? I have my 10 gigs coming in, and we've done that by the way. I backhaul 10 gig lambdas to a central point and I shunt down 100 gig out. Why? Well, I just saved 9 lambdas here. And it's worth to do the traffic. Now, obviously, can I do that in my network? Well, I don't know. We need to look at it. In their case, it was in Iberia. It did make sense because they had two internet peering points. So we could actually shunt the traffic over 200 gig and we could get out. If you have, let's say, 7, 8, 9, 10, 20 internet peering ports, it's not really going to, we need to think about another different architecture to help you out then. Now, remember I talked about the integration, and I have other slides. I kind of blocked them together. Packet layer, IP MPLS, OTN, ODU, switching and grooming. Not only switching, grooming as well. And then the WDM. Now, the WDM layer is actually the only switching layer you have where you can't really do grooming. Jeff and I will go look at that. I think that's about right what I said. But on the OTN, because we wrote, I know Jeff from a long time, and we wrote a paper a long time ago about switching and grooming. What does it mean? Now, having reread it again, OTN switching does switching, i.e. from an ODU2 to ODU2, ingress port, egress port, you can do that. We can also do grooming. I can do ODU2s into an ODU3s, into an ODU4. That can all be done in the same switching fabric. Now, I can also do switching on IP MPLS or on Ethernet, depending on what forwarding paradigm you're going to choose to switch on, or label well, I wouldn't want to say label, but on what field you're going to switch on. But you can also do grooming. In a way, if I said 10 gig out to 100 gig, I just did some packet grooming in a way. So I can do these, and that's basically this thing I want to explain. So now the question is, the router interconnect from here to here, I've shown you one example. It's not the only one. I can do black and white, hence the reason why it's black. I am an artist. So it's black and white or gray. Now, I can also go straight black and white into this port, for example. That's another alternative you can have. You don't need to go over an ODU switch, right? I can also have, for example, this transponder here, this pink one. I can sit it in here and go straight to the WDM layer, i.e. bypassing the ODU layer. I can. Now, why would I want to? Why you're showing me this, leader? Well, I'm showing you this for those customers that have TDM traffic, where packetization of a high bit rate, a high speed interface into packet, i.e. this goes in here, doesn't make sense. Why? Because it's S-word extremely expensive, and to do what? Just to packetize it and just to transport it over a network and then depacketize it again? Maybe there is a better way. Why don't we groom this stream in a higher order here, for example, with the packetized traffic, for example, if it needs to go to the other side, the same side. So there are some options that we can do here. I can't read that from there, so I'm going to do this. Okay, another extremely, I think it's very important and interesting is the multi-layer resiliency. Now, multi-layers, we talked about the cakes. We might have 1, 2, 3 layers, and then you have another, this is a P, for example, and you have PEs, then you have IP MPLS resiliency. You can talk about 1+1, 1-for-1, or rooted resiliency, or any other resiliency mechanism you have on each individual ODUK layer. And you can do some optical protection as well. We have a lot. Oh yeah, we have a lot. Which one is best? It's difficult to say. It's difficult to say. I mean, we really need to look at your SLA, what you've sold to your customer. How many 9s? This is something we need to look at. But at the end of the day, we do have a wee bit of a problem here. Well, what's the problem? If you look, G709 essentially, I don't know where I have to, let's forget this one. G709 terminates here. I have my optical supervisory channel that I can use to do some I guess, basic OEM, but there is no OEO, there is no optical, electrical, optical. It only happens here. I can look at the FEC. I can look how hard my FEC has to work. And if I look how hard my FEC has to work, I have a kind of an idea how, and mind you, people are gonna, yeah, but Lieven, there is this corner case. I know about it. Let me explain. First, the FEC has a very steep drop line, right? As soon as it works, and then there is this really, I don't know, knee, whatever, you know, the knee, and then it drops down, then it's it. So if you start working around this area, and you look and you go like uncorrected errors, for example, and you go like, shit, this is not working really well. Why is this important? Because if I can see that my line is degenerating, how do I tell this guy that his IP MPLS, he better shut this interface down to tell him, because something is happening. But shutting down an interface is like from the caveman, right? We don't do that anymore. We want to do it more intelligently. Now, why is this important, this FEC? Well, here's the problem. You're watching your telly, you have digital TV at home, and you see all these freezing on pixelization. Now you're going to call. So your whole neighborhood is going to call. The router guys, they're going to jump into the router and they're going to say, well, shit, man, my BFD is still up. I don't know, the line is still up. I don't know what the problem is. I'm telling you what the problem is. These uncorrectable errors, they were not BFD frames, because BFD loses one, loses two, and then the third one passes, my link stays up. My IP interface stays up. These were actually iframes that it lost. If you lose an iframe, you lose your anchor frame. Anything else is void, is irrelevant. So that's where you're the quality of experience for your users, at the end users, QoE, is not going to be so very good, because they're going to see all these funky things where they're going to, I don't like it. So what you want to do is actually, as soon as you're in that knee area, you want to say, listen, this is a signal degrade information situation. I'm going to tell my network management, and once, if it goes further, preemptively, I'm going to say this interface, bad interface, shut it down, and I shut it down. I can shut it down from here. I can actually send a message to him, and there are different ways of sending it. Or, well, rudimentary, you shut down the interface. I wouldn't do that. You can't. We do it. We do it, but I don't really like it. If you have MIPS here, you can actually use an OEM message. You can use a dedicated symbol, a FEFI, far end failure indication. Or you can use the MPLS unit that would be running here as well. Now the question I originally said, yeah, but Lieven, that knee, that can go very quickly. Yes, it is. And is it going to cover every case? No, it's not. But it's a tool that almost comes for free. It is for free, actually. That can help you out to alleviate these kind of nasty, those. Yeah, it's not broken, but it's half broken. It's not really black, but it's not white either. Those kind of gray situations where you want to have a solution for. That is one. So we've talked about that. Black and white, we talked. You can envision as well that it's a VLAN. A VLAN, what does that do? Well, normally it's a broadcast domain, but forget that. Actually, the VLAN is sparse and is put based on the VIT, VLAN ID, based on the VIT is going to be mapped to one trail or to another trail. So now we have a kind of a direction. And the nice thing is then that you can actually shape your bandwidth with the audio flex. Yeah, I say it right, audio flex, where you can, and I don't want to explain audio flex, but instead of rigid containers, we make them more flexible, right? So if I have audio flex here, I can adapt my bandwidth here. I make sure that my QoS, my port shapers are updated. If I say VLAN 10 on a 100 gig interface, VLAN 10 gets 150, I need to be careful, let me give you 55 gig. I need to make sure that I only spit out 50 gig to that VLAN. Anything else is not going to make it through here because my audio flex is let's say 150, is only going to be able to capture that much. So I have a pipe that is 100, I take a VLAN, I need to make sure that whatever the router shoots out maps into the transport. If there is no mapping and I shunt out everything else, well, some of the packets are going to get dropped to avoid that situation. So you need to have a significant QoS there to make sure that this port can do less QoS, i.e. less testing, less development, less testing, and so cheaper. Right, and yeah, okay, then that's pretty obvious. TDM into TDM, it stays TDM, right. And the other one is the model B. Now we have little or no lease lines, packet. And here we can envision, for example, the transponder sitting in here, or the transporter sitting into an optical extension shelf that is then managed as one. We can do again black and white. That would be the idea, because remember, if the transponder sits in here as I've drawn it, the slot economics, bandwidth and cost don't make sense. Now, does that mean we don't support it? We do support it, but I don't think we're going to sell a lot, but we do support it. So other way is to use something cheap, short reach. If you want to go long reach, you can. CXP, CFP, you can do that. 2 or 4 you can do as well. TDM, we talked about that. Again, multi-layer protection. I can have my signaling here. I'll feel here if something goes wrong. I can signal it there. And this way, I have my my OEM, my errors right in the router. The router can make a signal degrade, signal fail threshold decision and saying this is going bad. We have these ways. So what I want to say here, if my FAC is measured here, I don't need to signal anything. The router will make an decision. Okay, I have 7 minutes. So this is another representation of the single NE, the single network element. Before that, a lot of talk had to be done to make sure that the network was properly provisioned. Can I have that network? Well, I'm on lunch break now. Okay, then I'll send you an email. Can I, this type of communication you want to avoid. You don't need to go to 2 different network managers, or element managers. You can, in this case, you go through one and that's it. You streamline your provisioning. Now, I will glance over it. So this was a bit about hardware. I had thrown out my slides about what we do on the extended, with the PSC. I haven't talked about that, the photonic switch service engine, sorry. I haven't talked about the 400 gig. We've done a demo, and I'm sorry, we're running out of time. SDN, I want to really spend a little bit of time on that. SDN is the new Nirvana, and I would want to compare it as the we remember it was a PBT, the Nortel thing, where we say we don't need a control pen anymore. We use the simple switches and it's going to work great. Well, we know where that ended. So the other thing I want to say is the MPLS TP. We've seen a massive amount of interest, and we hold off our boat very long because we were thinking it's not standardized. We don't know where it's going. Remember the history without MPLS TP, or TMPLS, it should say. I don't know if you know, I can tell it tonight over a beer, but at the end of the day, the IETF claimed their ownership of the MPLS TP, or the MPLS Ethernet, the E-type, so it was theirs and the ITU could not touch it. The point I want to make is that we've seen a massive demand. At the end of the day, we're kind of like, okay, yes, we will do TP, and now the demand is dropping. I don't know, it's very weird. Is it because we have it and nobody bugs us anymore? I don't see it. The other concern I have is that, do you want to use it in the core? I don't know. But that's the TP discussion. Again, a topic I haven't covered here. Now, for SDN, so where are we? SDN has been, I think it's great in data centers. I think it's really, it's unbelievably cool, no? I think it's cool. Yeah, it's really cool. Should we do it in the transport? Oh yeah, we can do it in the transport. It's just some optical cross connects. Simple, Somebody in the Open Network Forum wrote some extensions to the OF, the Overflow Protocol, and that was it. And then somebody stood up and said, excuse me, sorry, ODU? ODUK? Oh, yeah. Yeah, we're just going to model that as a port. So, okay, let's form this new transport group. So they're now doing the new transport group. And now they're going like, whew, man, what did we start? So they have a little bit of a concern, and the board of the OpenFlow apparently doesn't really like the progress, or the lack of, that the new transport group has made to actually define a clear use case, a clear way forward. How the heck are we going to do this? What are we wanting to do? What's the problem we're trying to solve? And we know that the answer is OpenFlow. Well, yeah, I don't like these type of situations, right? Whatever the question is, the answer is OpenFlow. Well, hang on a minute, let's be smart about this. So I think we need to do a little bit more soul searching and really understand what we're trying to find and solve with OpenFlow in the transport layer. Let me be more precise. In the multi-layer transport layer. It's multi-layered, remember? It's not a single layer. Because for data centers, it may be IP, at best IP and PLC, I can deal with that. And here we're talking about the 3 layers, fundamental layers, because you remember, My ODU can spawn into different layers. My IP-MPLS might spawn into different layers as well if I do hierarchical LSPs, for example. So it's not that easy. So where are we? Well, and I wanted to show you this, but I didn't put in the graph. So this is an easy, relatively easy thing. It's OpenFlow can do this with a very limited, I use the right word, set, and limited is a bit of sarcastic. It is not that limit. Set of actions, I forgot the name, actions, but once you put this G709, and this is multi-layer, by nature it's multi-layer. If you add this to this, you go like, let's swallow this one and have a beer and think about this. So I'm not sure that as an own SDN, i.e. SDN controlling the multi-layer transport makes sense. Now, that's one opinion, and I share that one. The other one is like, what if we look on what we've already done? The separation of the data plane and the data plane and the control plane is not something that the SDN guys from university, and I don't want to offend anybody. I am from Belgium. I'm quite outspoken about my thoughts, unfortunately. But you know, where is the experience that has been gained over 20, 30 years? Remember, where we are now. That certainly somebody from university says, listen, you know. This is the solution. It's completely new, but it's not. The separation of the control plane and the data plane has been done before. Think about SS7. Think about the GMPLS. We've done it before in my lifespan, right? What I think we need to look at is multi-layer, and my stokpaardje, I don't know how you say that. It's basically my favorite topic. Is basically SDN in a multi-layer, dynamic multi-layer optimization environment. And there you can get me going. There I go, like, oh yeah, I love that. Because, let's be honest, although internally we're not agreeing, this is my personal opinion, I must say. If we could look at the multi-layer, let me do this, and we can look at the state of the network. We know the topology, that's easy. But we also know, per network layer, what we're actually shunting over, what we're transporting over each trail or LSP, as you want to call it. I don't care. Let's look at that. Let's look at that and let's analyze it. Once we can, if we have it, and I call it, and again, I'm offending probably, the brain, I call it God normally, but let's say the brain sits here and it looks at it and it sees these network and it sees all these things flying back. The brain says, give me the information. And all these, there are monitoring points, not like Armand, but a little bit more intelligent, that shunt up the traffic to the brain. And the brain says, I don't want to deal with it, you deal with it. And it's collecting. And there is another brain, it's a big brain, there is another brain that says, listen, you know what? I have a cost optimization function. Which one? Cost could be hop count, could be delay, could be anything. But he does this, he gets all this resource information and state information and usage information all the time in continuously. And there is this other little brain that continuously says, oh, hang on a minute, no, it doesn't make sense. Oh, stop, it now makes sense for, I'll make this up, this LSP that goes like this, let's make it worse, that snakes through the network. It doesn't make sense anymore to do that because my cost optimization function says, pull an optical lambda there, or use a new DU trail, I don't mind. But the cost optimization, the message is here. This little brain does the cost optimization and says, listen, it's actually now more interesting to do this to your network. Obviously, it needs to be cheaper, right? Hence the cost name. It needs to be cheaper, whatever cheaper means in this context. And then you do this. And in the meanwhile, the data kit's coming, and you know, on Spring sits there. And the traffic flows, and then it gets night, and people are doing other things. Traffic shifts around the network, and then suddenly the traffic, the measuring points come in, and this little brain was like, "Hang on a minute, it doesn't make sense anymore. We need to do something else now." And I can see then that the network is then being provisioned from a centralized point, either at the ingress and let GMPLS take care of it, or via an SDN way. I can kind of see that happening, or maybe only at the ingress. We pre-provision these trails, and we say, listen, this tuple now needs to go into this LSP because I know that's a good cost, and this tuple, slightly different UDP packet, for example, needs to go over the snake way, for example. So these are the way that I can see happening. Now the problem is to define this cost function. I actually made a little animation out of it, but it's basically the same thing what I wanted to show. I am running out of time. In summary, what I've told, these are the things that I'm working on, together with the boys in the optics, together with these standards. IRS is another standard for, I don't know, was anybody of you guys in the ITF, the last one? No? Were you in the IRS meeting?
No, it wasn't.
Okay, well, you didn't miss a thing. It was clear as mud. I was really, and the room was full, and everybody was like, "What's it gonna be? You know, what's it gonna be?" And then it was like, we're not gonna define Cisco. We're not gonna define any protocol. Defining protocols is very bad. We shouldn't do that. We should first write down the requirements. But we are thinking about netconf. Well, hang on a minute. You just what is it now? Is it netconf? Is that the answer to the question? And what is the question in the first place? So it was very flu, very bloated. But I'm sure they will find something. And another thing I find with SDN is the right thing to say. If you don't talk about SDN, like me I'm doing now, you're not from this earth, right? Where were you for the last couple of months? So you need to talk about it. But everybody talks about it, and you can see it. Broadband Forum, the ITU, IETF, I'm forgetting one, OF, they're all talking about virtualization and separation of these two things, which is great. And they're all saying, well, it's mine. No, it's mine. No, it's mine. And you can see this political, pulling going on where you go like, guys, what are we trying to solve and how is then later? But anyway, so this is my opinion. My name is Lieven. If you have questions, don't ask them. I'm joking. If you do have questions, I'll be happy to answer them in the hallway. I do think we have a break now. Or do you have questions now? Sorry.
Yeah, please, questions for the
No, cool. Thank you for your attention, guys. Appreciate it.
So we're also talking about SDN tomorrow morning. So.
Oh, okay. Yeah, I'm sorry. I'll be there. I promise. I can.
So yeah, we're having a break now. So we come back 3:45.
He's focusing on the other side.